Hello, in this video we are going to have a look at a very special application of using that combination formula. So let's get started, and I want you to take this starter activity really seriously. Don't skip it, and just do what I say, because that sort of process of discovery is really important. So you can see here I've given you 4 calculations: 3C0, 3C1, 3C2 and 3C3. I want you to use your GDC to plug those values in and see what numbers you get out. So absolutely pause the video and then do that activity, then come back. Okay, I'm really hoping that you did that. What did you get? Did you notice anything about them? So 3C0 should have given you 1, which kind of makes sense. I'm choosing none from 3. There's only one way of doing that, is to choose nothing. 3C1 gives me 3. Okay, so if I've got 3 items, and I'm choosing one of them, I either choose that one, or that one. So that kind of makes sense anyway, but your calculation should have given it to you. 3C2 gives you 3 as well, and 3C3 will give you 1. If I've got 3 and I'm choosing 3 and the order doesn't matter, there's only one way I can do that. Let's pick all 3. So you've got 1, 3, 3, and 1. Now, do those numbers look familiar to you at all? I hope they do. Have a think about it. Pause the video again if you need to. Where have you seen those values before? Okay, if you're thinking straight, you might recognize that those values are the row of values of starting coefficients when using Pascal's triangle. So I'll do it in blue up here. Just a reminder that we've got 1, let me zoom up a bit more so you can sort of see it. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. There's that row. 1, 4, 6, 4, 1, and so on. You can do Pascal's triangle for as long as you want, and in every instance the row gives you a plus b to the power of whatever row number it is, starting from row 0. So this is a plus b to the power of 0. This is a plus b to the power of 1, which would be a to the power of 1 plus b to the power of 1. This would be a plus b to the power of 2, a plus b to the power of 3, a plus b to the power of 4, and so on. That's how it works. And do you remember how Pascal's triangle works in terms of how we expand? I wonder if you do or not. Let's just deal with 1, 3, 3, 1, and we'll go through that to remind you. So this is the starting coefficient. So we go 1, and then we would take the left hand of the plus sign, I suppose, and we would raise that to the power of the highest power. In this case, it's 3 because it's on the third row. And then b would be raised to the lowest power, which is 0, and b to the power of 0 is just 1. So it's implicit. It's not explicitly written down. And then we would go plus 3, and then we would have a, and then we drop down 1, and then b goes up by 1. So b to the power of 1, and the 1 is implicit, so we just write b instead of b to the power of 1. And then we would have plus 3 ab squared. So a has gone down 1 power to a, and b has gone up 1 power to b squared. And then finally we would have 1 multiplied by a to the power of 0, which is just 1, so we don't write it in. And then we write b to the power of 3, it's gone up by 1. So that's a reminder of how Pascal's triangle works. And it turns out that these combinatorics here become those starting coefficients. So let's have a look at it in general, and then we'll have a look at a couple of examples to finish off this video. It's called the binomial theorem. It looks more complicated than it really is, so wait till you get to the practice and you'll see it. A plus b to the power of n can be expanded into, so note here, the power of n doesn't change. So it's nc every single time, nc. Then we start off with 0, and then we're just going up by 1 each time. nc0, nc1, nc2, all the way to ncn minus 1. And then the last one would be ncn. NC0 is always 1, NCN is always 1. So it's always starting and finishing with 1, again, which makes sense from our combination work. And then you can see the powers of A are going n minus 1, n minus 2, all the way down to 1, and then 0, which of course we know means that it's equal to 1, so we don't normally write it in. And B is reversing, so it goes 0, 1, 2, all the way up to n minus 1, and then finally to n. So you might notice this little pattern here, that this value down here is always the same as the power of b, implicit there. This power here plus this power here will always equal this. So if I'm looking at NC2, I can immediately go b to the power of 2, and then I know that a must be n minus 2. So when I add those together, I get n. And we'll see that in the example as well. So why would we use this when we've got Pascal's, I keep on saying Pascal's triangle, and it always reminds me of Pascal lollies, like Pascal marshmallows, which always makes me feel hungry. Anyway, it's not Pascal, that's double L, it's Pascal, which is a single L. So Pascal's triangle. Why would we use this instead of Pascal's triangle? Well, in Maths Methods Foundation, the highest thing I think we can ask is to the power of 5. So it's actually not that hard to do Pascal's triangle, to be fair. But we could be using this expansion for a plus b to the power of 17 or something like that. And doing Pascal's triangle to 17, although doable, is rather inefficient when this will do the job for you in a single line, and then a bit of calculator work. So that's probably why it's worth at least seeing the binomial theorem exists, even if you don't tend to use it, and you may not use it in the exam even, but at least you know about it. And it is part of the course to know about it. Shall we look at a couple of examples, because that'll make it really clear. Example 1, expand x minus 2 to the power of 5. Okay, so we know that we could do this using Pascal's triangle, but let's just see how easy it is to do the expansion by the binomial theorem instead. So we've got x minus 2 to the power of 5 is equal to 5c0, x to the power of 5 minus 2 to the power of 0, plus 5c1, x to the power of 4, just going down by 1, minus 2 to the power of 1, plus 5c2, x to the power of 3, just going down 1 power, and then the minus 2 has been going up 1 power. What else have we got? Plus 5c3, x to the power of 2, going down 1 power, and then minus 2 to the power of 3, plus 5c4, x minus 2 to the power of 4, plus 5c5, x has disappeared, or x to the power of 0 if you want to put it in, and then minus 2 to the power of 5. And we're nearly there. Again, just to point out, this number and this number agrees every single time. This number stays the same. And if I add these two powers together, I get 5. 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3 is 5. 1 plus 4 is 5. 0 plus 5 is 5. So they're always adding up to 5. So you can always check to see that you're getting it right. Okay, then the next thing I will do, I'm not going to do the full solution for you. I'm just going to do this next line. I'm going to leave 5c0 and 5c1, etc., just where they are, because it's a calculator operation at that point, or you could use the NCR formula in order to calculate it by hand if you needed to. But just to make this video faster, I won't. But I'll just do the powers underneath, the power bit. So this bit here is negative 2 to the power of 0. So that is that's equal to 1. So we would end up with, sorry, I'm just, my pen has just lost its connection, so I'm just going to quickly sync it back up. So I would start with 5c0, which is just 1 we know, x to the power of 5, plus, now we've got 5c1 there, so that's going to be some value, it's going to be 5. But anyway, I'll just leave it as it is. So 5c1, now minus 2 to the power of 1 is minus 2. So I'm going to end up with a minus here. So I'd get minus 2, 5c1, x to the power of 4. Now the next one is minus 2 to the power of 2, which is positive 4. So I'm going to end up with plus 4, 5c2, x cubed. And the next one I've got is minus 2 cubed, which is going to be negative 8. So whenever it's a negative number raised to an odd power, it's going to be negative. So it'll be minus 8 5c3 x squared Moving on, minus 2 to the power of 4 is 16, so it's plus 16, 5c 4x, and then I'm going to have minus 2 to the power of 5, which is negative 32, so minus 32, 5c 5, and x to the power of 0 is 1. And then I will just simply work out what those C values are effectively, multiply it by the number in front of it, 2, 4, 8, 16, 32, and that would be my final line. Okay, let's have a look at example 2. I'll keep it zoomed out now so you can see the whole thing at once. This is where it becomes a little bit more efficient than doing Pascal's triangle, even for the lower order ones. I had never seen an exam question which asks this, but technically you could be, so I'm going to go through it just to make sure. And it says, what's the coefficient of x cubed in 3 plus 2x to the power of 7? So we could expand it all, and then once we've expanded it all, work out what the coefficient of the x cubed term is. But instead of doing that, we can sort of just move to straight to the term we're looking for. So x cubed term is what? Well, looking at it, x is in the second half, so we know that means that the powers are going to go up. So it's going to be x to the power of 0, x to the power of 1, x to the power of 2, x to the power of 3. So we're going to have an x to the power of 3 at that point. So we're going to have 7c3, okay, because that and that will match. But then we've got the first term, sorry, it should be 2x, shouldn't it? Because it's 2x to the power of 7. So the second term is raised to the power of 3, because it'll give me my x cubed term. And the first term, which is 3, is going to be raised to the power of 4, because 4 plus 3 equals 7. Okay, see how that works? So I work out the 2x to the power of 3 is where it's going to be. Then I can fill in the 7c3, because that's always going to be the same as that. And then I know what the first term is going to be raised to the power of, because it's always going to match there. Okay, so now I can just work that out. I will do this one this time. So I'll go to my calculator and I'll see that's 7c3. I'm going to do a few switches between screens to do this. So NCR73. So that will give me whatever that value is. I'll do it, but you don't need to. So it's 35. So I'll type in again, NCR 7,3. And then you can see I'm multiplying it by 3 to the power of 4. So 3 to the power of, oops, I don't know why I've got x there. 3 to the power of 4. Should be a time symbol in between them just to make sure. Multiplied by, switching back, I now have a 2 to the power of 3. So 2 to the power of 3. Let's return 22,680. So it's 22,680 x to the power of 3. So the question is, what's the coefficient of x cubed in that expansion, i.e. the coefficient, oops, you can't see what I'm writing, i.e. the coefficient is 22,680, and you're done. So in the textbook, you'll be just asked to do some expansions. There may be some problems a bit later on, but I don't think I listed them as ones you have to do where you need to find out a particular coefficient. So please feel free to practice those, because they are quite useful to do. But ultimately, what I want you to at least have access to is the capacity to expand using binomial theorem. Now, just in terms of the exam, from what I can tell, I've only seen questions which are along the lines of use Pascal's triangle or binomial theorem to expand the following, and it might be something like x plus 2 to the power of 4 or something like that. So that tells me that you can use Pascal's triangle and it's not a problem at all. But if you practice this and you find that this is actually really useful just to go bang straight into the answer, please feel free to use it. And who knows, maybe this year is the year that they'll say, use binomial theorem to expand, and therefore you only get 2 out of 3 marks if you don't use binomial theorem or something like that. So it doesn't hurt to actually do a bit of practice around it. Okay, that's enough for this video. Thanks. Oh, the code word, I forgot about that. What's the code word? Well, if you go back to the start of the video, I mentioned a particular kind of confectionery item, a particular kind of lolly. Email me what that is and you'll get a prize.